So today we will learn about this chapter 4, mathematical expectation. So expectation is quite related to the notion of this mean. Okay, so mean or average would be familiar to you guys, I think. So if we have 1, 2, 2, 3, 5, and 6, and then what will be the mean? So mean will be, let's see. Yeah, let's say the temporary mean as 3, and then minus 2, minus 1, minus 1, 0, 2, 3. Okay? And then we just cancel them out, and then we just have plus 1. And so we just add to this temporary mean with this 1, 6. So that's the true mean that we computed from this measurement or our observation data. And then, yeah, today we will talk about this notion of the mean and then a generalized concept of this mean. Okay, sorry about the delay. So this is our sample space, right? Which has these unique entries. But from this sample space, we can observe this. But from the dice case, we can think of the uniform probability, where each of these outcome that we have in our sample space can have like the equal probability of 1/6. But yeah, we manipulate our dice so that we have like a different probability values. So from here, we can see 1 as 1 times out of 6 trials, but for 2, we observe 2 times. So let's say the true probability associated with this value 2 is 2, 6. Okay, and then 3, 4, 1, 6, and 4, yeah, is actually having a 0 probability. So although the dice has the value of 4, but we carefully manipulated it so that we never see the value of 4. And 5 and 6 as like this, yeah, just like normal 1/6 of probability values. And then in this true probability distribution, we can compute the expectation or the mean value. I mean the true mean by considering these probability values associated with each outcome in our event space. Okay, so in this case, how we compute the mean is this. It's actually the value from our random variable or outcome times the probability, right? Plus 2 times 2/6 plus 3 times 1/6 plus 4 times 0 probability, right? 5 times 1/6 plus 6 times 1/6. Okay? So mathematically, that is called this expectation, an expectation of the random variable x. Okay, so our random variable x is the outcome from our event space S. Okay, so each of these value will be one instance of our random variable x, and then its expectation value is computed in the exact same manner like this. Okay, so in this case, their mathematical expression is represented in this form. So we multiplied the value x, which is the random variable value, times the probability. So f of an x is representing the probability distribution of random variable x. Okay, and also here the large or capital X and small x. Yeah, you guys know the difference, right? So this is the random variable itself, and then x is each instance. So x is either 1, 2, 3, 4, 5, or 6. Okay, and random variable capital X is the random variable itself. Okay, so this is the mathematical expression or definition of this expected value or expectation. And this was the discrete case. And then in the case of continuous case, we just simply replace this summation notation into this integral notation, right? So we have infinitely many values, and then we we just do the same computation and then do this integral to compute the expected value of x or expectation of x. Okay, and then from this case, the x had a range between 1 to 6. So x can never be 0 or even minus, it cannot be -1 or -2, right? But in this case, it has no limitations in terms of that range, as well as in this integral part. So we always perform the integration over -infinity to infinity, right? So the reason for this being always true, I mean, why is this true all the time? It is because we consider the probability distribution as having, so in the case of 1 through 6, so we can think of the probability that is defined over all the regions of an x from -infinity to infinity. And then for those ranges that are outside of the possible values, so less than 1 or more than 6, we have a 0 probability. Okay, so if we can define this probability distribution or probability density function f4 of an x in this way, and then we can always obtain this expression, or this expression of or definition of the expectation is always true. So the probability distribution will be something like this. Okay, so we chop them off at this point, and then we get 0 values after 6. Okay, and then we can kind of extend this notion of the expected value or expectation into an arbitrary function of x. Okay. Okay, so we think of the function of x, which is a random variable, as, for example, x, maybe 2x squared minus 3x minus 1, for example. So this is a function of an x, right? So if we had the event space of 1, 2, 3, 4, 5, 6, and then you guys know how we computed this expected value, right? The value and then its associated probability. So we do the same thing. So here in this case, we do not just use x as it is. We just use this g of an x. So for 1, so we can compute it as -2, right? So for 2, 8 minus 6, was it 1, right? So that way we can transform or map these values by using this function g of an x, right? And then these values times the probability that this guy had, okay? So we basically replace this 1, 2, 3, 4, 5, 6 into those function values of -1 and 1 and g of x equals 3 and so on. Okay, so that's how we can extend this expectation into a arbitrary function of random variable x. So mathematically, we have the same expectation notation, and then inside of it we have this g of an x. Okay. Okay. So for example, what would be the case, or what would be the example of using this g of an x instead of an x? Okay. Okay, and then, so suppose, we are using those height and weight, which is kind of a standard example. Okay, so out of all of our all the students taking this class, so you guys have your own height values. So some student might have 170 centimeter, and some other student may be 175 centimeter, right? So that is that can be viewed as this x itself. Okay, and then we collect all the unique values. So from our observation, the two different students might have the exact same like the height, right? But we think of this event space where we only allow the unique entries. There is no redundancies, and then we can just boost or increase the probabilities associated with the same value that are frequently appearing. Okay, so in that case, we can just compute this average or expected value by considering each of these unique value and its associated probability, right? But now we want to compute the probability or the expectation value of our mother's height, for example. So our function g of an x can be considered as mapping your height into your mother's height. Okay, so in that case, 170 centimeter could be like 160, and then 175 could be 148 or something like that. Okay, so in this case, the probability, this kind of a mapping should be unique. So yeah, as I give this example, it may not be the best example, but we can think about this kind of a mapping from the original random variable x into some other numerical value or some real number. Okay, using those real number from these original values to this mapped value. So instead of using this, using those and then associating them with the same probability distribution, and then we can compute the expectation of this g of an x. Okay, so here in this case, g will be the mother's height, for example. Okay, and then instead of an x, we just replaced x into g of an x. Okay, we can extend that concept into a joint probability. So now we can think of this function of x and y. So function g, so function is basically just rectangle. So you can think of this black box, and then you give some input to this function, and then this function will give some kind of an output. And in this case of g of x comma y, and then in this case, you always give the input as the pair of x comma y. Okay, and then after using this function, after passing through this function, you will get a single value. Okay, not a vector or multiple values. So you give two numbers of an x and y, and then you will get a single number. Okay, and this mapping has a certain rule or certain kind of transformation, like mathematical expressions. So for example, x squared plus y squared minus 1. So this function g of x comma y can have this mathematical expression. Okay, so in that case, if we put 1 comma 1, and then we will have 1 comma 2, we will have 4. Right? And then we think about the probability distribution that is associated with this x comma y. So we consider two variables at the same time. So we think of the joint probability. So the probability of x comma y being 1 comma 1, let's say that probability is 70%. So for this probability will be 30%. Okay, and then we just simply compute the expectation, just like the same manner as we saw in the earlier slide, like this. And then so this is our answer for this expectation value, or the mean of this g of x comma y. Okay, then since we have two values, we have this double sum. Okay, so this double sum, the meaning of this double sum is that you consider all the possible x comma y values. Okay, and then in the continuous version, we change them into integral signs. Okay. And then now the variance and the covariance. So variance and then the standard deviation. Yeah, I believe you guys are already familiar with these standard deviations and the variance. So up to this point, it might be boring, but yeah, I think you guys have to be really familiar with all these expressions so that you can easily extend it, and then yeah, so then you don't lose your track in understanding a little bit more complex version of these. So in this case, let's look at this expression a little bit more carefully. So in this case, from the perspective of an expectation that we learned in the previous slide, it has the same notion where we see the function g of an x is defined in this manner. Okay? So in this case, we are basically computing the expectation value of this measure or this function value, okay? Because we are just multiplying its associated value, I mean the probability value. But in this case, in this specific form of x, g of an x is defined in this manner. So for every value, so 1, 2, 3, 4, 5, 4, 5, 6. So we consider the probability of like 1, 6, 1, 6, and was it 2, 6? And 0, 1, 6, 1, 6. Okay, and then we can compute the mean, right? The mean was 3 plus 1, 6, right? So suppose this was the true mean of these probability distribution, and then we just subtract this value from each of these values. So that's x minus mu, right? And then we just take the square of it, and then that value is multiplied with this associated probability value, and then we just sum them up, and that's how we compute this variance or this specific type of function g of an x and its expectation value. And then if it's change it to a continuous version, and then we see the integral sign here. And then if we just take the square root of these values, and then we call that as a standard deviation. So far, nothing special, and I think you guys are already familiar with all these notions. So let's see. So before, so here up to this point, so this is basically the main. So the main thing that we have to learn about this expectation value. But let me add a little bit more intuitive understanding about this expectation. Okay. So here in this case, so f of an x is our probability distribution. So it always sum up to 1, right? And then it can never have a negative value. So it should always have a positive or 0 values, right? And then in that case, it can be viewed as, so we have g of an x, and then f of an x. So this is our probability distribution, PDF or something. Okay, so in this case, it can be viewed as the interpolation of this g of an x. Okay, so interpolation. So I'm not sure if that is the exact English word that I meant, but in Korean there is something called interpolation, extrapolation, interpolation. Let's see. So something like this. So we have 1, 1 here, and then 3, 4. And then we know the centroid, right? So centroid is 2, 2.5, right? What about 2 to 1 of this ratio? So this ratio of 2 to 1. So how can we compute this value? So we can simply 1 times, we just sum them up. Plus 2 times 2 over 3 divided by 1 over 3 plus 2 over 3, or 1 times 1 plus 2. It's not a good example, I mean, in terms of the numbers. So, but we divide those values by 3, and then we multiply this guy with this value, and then this value times this value, right? So that is called what? 뭐라고 그러죠 이거? 한글로 뭐라고 그러죠? 내분점. So so this is called in Korean 내분점, or I believe that is also translated into English as a interpolation. Okay. And then what about this? So I cannot easily draw a little bit more interesting example, but what if we have 3 values? So so back to this example. So we have 2 values, and then their weights. So 1 is associated with the weight of 1 over 3, and 2 is associated with weight of 2 over 3, right? And then those weights are always summing up to 1, right? So it's like this. So if we extend it into a version of multiple points, so we have like 3 different points, and then each of these points will have its own weight value, okay? And then we can think of this interpolation in a straightforward manner as this weighted average, okay? So we have like these 3 points, and then this was 1, 2, like 4, 3, and 3, 5, and then we just consider the x value, and then we just weight this guy with 1/4, and this guy as maybe 2/4, and this guy also as 1/4. Okay, and then it will be something like this. So somewhere around here. So it's twice. I mean, it's twice as close to this point because it has twice the probability or twice the weight compared to other values. So these guys will have the half weight, which is 1/4, compared to this guy, which is 2/4, right? So in that case, the resulting point and its x coordinate can be computed in this form. 3 point, right? So this is our resulting x coordinate when we gave the weight of 1/4 to this, 2/4 to this, and 1/4 to this. Okay, so this is viewed as another interpolation or 내분점, just like this. Okay, so we only have 2 points, but in this case we have many points. But this type of probability is actually telling us how we distribute our weight into each of these points. But all the weight, I mean the summation of all the weight that we can give to all these points is always 1. Okay, so we have like a 1 kilogram, and then we have to distribute some amount to each person. It could be some kind of meat or really money. Okay, and then we have to really decide how much we should give out of the limited budget or limited amount that we have. Okay, and then these can be viewed as the probability distribution, and then these probability will give the weight to each of these values of 1, 3, and 4. Okay, so that is a little bit of an intuitive understanding about this expectation value. So these are something like 1, 3, and 4, which is our coordinate, like these, okay? So 1, 3, and 4, which are the value themselves, and then those probability value will give the weight, okay? But the summation of all these weight is always 1, okay? So in that sense, it can be viewed as this kind of interpolation or weighted average of this g of an x. Okay. And now we have this interesting relationship. So sigma squared that we computed from in this equation, that is the same as the expectation of x squared minus mu squared. Okay. So in this case, it can be viewed as, so yeah, from this example, so it's a little dirty, so let me change the color. So yeah, let's recall how we computed the variance in this case. So this g of an x, which is a transformation of an original x into some other value, and then we have to basically subtract from each of these values by this amount of a mean, right? So we have to first subtract each value to by this mean, and then we have to take the square of it. So this kind of computation could be a little bit burdensome. So in that case, we can just simply compute the expectation of x squared. Instead of e of x minus mu squared. So in this case, we first had to subtract mu from each of x value and then take the square of it. But we just square those values. And then we just simply compute this weighted average using this probability distribution. Okay, and in that case, after computing this, we just simply subtract 3 plus 1 6 squared. Okay, so in that case, that value will be exactly the same as the variance. Okay, so this equation is what is related in this case. Okay, and then so you guys remember how we extended this expectation of an x into g of an x, right? And then this guy, we have this. So this was expected value or mean, and this was the variance. But this was a expected value of g of an x instead of just an x. So we can exactly extend this guy into the notion of the variance of g of an x. Okay, in that case, we just simply extend it in this form. Okay, so which is just this guy. So from this point, the notation becomes a little bit non-trivial or a little bit tricky. Okay, so in this case, g of an x is straightforward. It's a function of an x, but the mu of g of an x, which is placed in the subscript of this mu, that means the mean value of this guy. Okay, so this guy, mu of g of an x, is the same as this guy. Okay, so this is another notation, but compared to this, so this one is a little shorter and simpler. So often we use this guy in order to represent the mean of g of an x. Okay, so in this case, we just plug this guy in, like this guy into this part, and then yeah, it is the same as this guy, and then g of an x minus this guy squared times this f of an x, which gives weight values to each of these values. Okay. So in the case of like mapping from our own height into our mother's height, and then we have our own mean, right? So we can, suppose our mean value for our height was 165, for example. But if we think about our mother's height, and then our mothers will have their own mean value, right? So in that case, the mean, suppose that mean was 160. And then we have to subtract each of our mother's height by this the mean value of our mother's height. Okay. And then now we learn about this covariance. So probably I think the covariance is the new term that we haven't learned in high school. So I think you'd better paying attention from this point. So in the case of covariance, so you guys know the variance, but in the case of variance, we can just rewrite the variance in this form. So it's square of this value, right? Oops, this guy should be x. But in this original definition of variance of an x, we can change one of them into some other value y, and then its own mean value. Okay. So in that case, we call that as covariance. So like this, in terms of definition, it can be written as this form. So in this case, it is just a one specific example of this guy. So we learned about g of x comma y. So in that case, we considered its associated joint probability of x comma y, right? So in that case, let's see. So in this case, so we learned about this joint expectation value. So we consider x and y at the same time, and then our function g of x comma y takes the input of x comma y, and then generates the output of a single scalar value. And then for this value, we associate its joint probability of being exactly x being 1 and y being 1, and then we consider the probability of observing this jointly x comma y as 1 comma 1, and that probability was 70 and this probability was 30, and then we just take the weighted average of our values from our function output, right? So this was this joint probability and joint like mean or expectation value. And then as g of x comma y, we actually define our g of x comma y into this form: x minus mu x times y, let's see. So this definition, right? X minus mu x times y minus mu y. So when defining our g of x comma y into this form, then we call that as covariance of x comma y. So this part is our g of x comma y. Okay, so So yeah, basic interpretation of this value is that, so what is the meaning of the variance of an x? So the meaning of an variance is that on average, how far the x value is from your mean value. So suppose your mean was 170, but you sample a person randomly and then consider their height, his height or her height. And then if the variance was, or the standard deviation was 5 centimeter, and then on average, whenever you obtain one sample or one person, and then the average distance from the true mean, which is a 170, will be 5 centimeter. So your sample is on average 5 centimeter away from your mean value. So if your mean is 170, and then on average, you will see the person of a height of 175 or 165. Yeah, you could have, yeah, you could see like closer instances to the mean, like 171 and 168, which has a less distances than 5 centimeter, which is our variance, or I mean the standard deviation. So that is the meaning of the variance. Okay, but in this case of a covariance, it is the same. So you jointly sample x and y. Okay, and then x has its own mean and y has its own mean, and then they will have their own differences from their own mean, right? And then we just, so from the variance case, we just consider the squared value of it. So on average, we have, each instance will be 5 centimeter away, but in the case of variance, it will be 25 centimeters squared away from the mean value. So that squared value was the meaning of this variance. But in the case of covariance, it is really the same. But you now use the two values jointly, x comma y, and then you consider their own distances from their true mean value, and then just like we squared this average distance, like 5 to 25 centimeters squared, we just multiply these two values together. Okay. So on average, this guy was like, so suppose this guy was man's height and this guy was women's height, and somehow, so in this case we really have to consider the joint probability. So in our sampling process, we always sample one man and one woman. Okay, so we do not consider them separately, because they are existing in this joint space. So for example, yes, so our parents, so each of your parents, so your mother and father always have two children, where one is like boy and the other is girl. Okay, so we follow always this kind of rule somehow. Okay, and then for each of these pair of men and women, I mean the boys and girls' height, okay, and then we can consider their own mean value, and then we consider their average distance from their own mean, and then we just multiply them together from this pair of values. Okay, so so in that case, so intuitively, if our parents were a little taller than any others, and then both of their boys and girls' height will be taller than their own average values, right? In that case, they are jointly far from their mean value. Okay. In that case, this type of a covariance value will have some non-zero values. Okay. So in that case, the boy and the girl's height, since they are born from the same parent, they are somehow related, right? So if their parents were tall on average, and then both of their boys and girls will be taller, right? But what if we just randomly sample two person, where one is a man and one the other as a lady, okay? So men and women's height, we just sample them independently, and then their covariance value will be actually 0. Okay, because in that case, the two samples that we obtain for men and women, so their measurement or their height is not related. Okay, so in that case, suppose I picked up one person and that person was really tall, 190 centimeters. Okay, and then you just independently or separately sample another person, which is now a woman, okay, and that woman's height was, it could be like 160, 150, or 170, and so on, right? So the distribution of that girl is not dependent on the man that you previously sampled. So in that case, those two values will have, will have 0 covariance. So in that case, we call that situation as uncorrelated. Okay? So in this case, the sample should be really related or dependent. So if one gets bigger than its own average, and then the other should be also bigger, or it should be smaller. In that case, they are somehow correlated, and their pattern of pattern about how far they are from their own average is actually dependent on each other. So in that case, this covariance value will be non-zero value, but in other cases where the two samples are like separate or independent, then their covariance value will be 0. So let me explain a little bit more about this phenomenon. So in this case, suppose this was the man's height, and this guy was woman's height as well. So if they were like separate or they are independent, and then you got somehow lucky and your sample for this man's height was 185. Okay, in that case, this term is fixed. How? Suppose the mean was 170, and then this value is plus 15 centimeter, right? And then this value of y minus mu I. So let's consider the situation where we already sampled a man's height as 185, and then you sample another woman, okay, and then the distribution of that woman's height will be just like, so suppose this value is 165, for example, 165, and then you basically perform multiple sampling. So you sample over and over, but you basically assume the first sample or the man's height was fixed as 185. And then if this probability distribution is exactly around or exactly centered at the true mean of woman or mu y as 165, and then so basically the distribution of y given the man's height was 185, and then that distribution is exactly centered at 165, which is a mean of y value. And then here in this case, so the summation of over y value will have exactly 0 value. So that way, that's why we get 0 covariance value in this case. Okay, because if we sample this woman's height, and then this value will be minus 10. If we sample here, and then this will be plus 10, and this value will be minus 3 centimeter, and then another plus 3 centimeter. So if our probability distribution is exactly symmetric or centered at the true mean μy, and then their covariance value is 0. So here, the main difference is that in the case of variance, those minus value and plus value, or the minus difference or plus difference, was actually squared. So that way, they were all contributing as positive numbers into our variance, right? But in this case, those difference, whether they are minus or negative value or positive value, they will be contributed with their own sign values. So in the case of minus values, they are no longer squared. So if they are centered at the original mu y, then when x is fixed, then this value will exactly generate the 0 after we perform this summation. Okay? And then what if the previous case where what about the previous case where the parent, so we only observe or we only sample man and woman's height from the same parent. Okay? In that case, suppose our sample for man's height was 185. Okay? But this woman's height, the average value or mean value for woman's height will not be changing. So they will remain as 165 because it's actually marginal mean, or it's actually the mean that does not consider the x value itself, right? So in that case, this 165 is still the same, but what will be the distribution? It will be biased towards the positive value, right? So that their mean value will be likely more than this 165. So that's kind of our intuition. So if their parents was really tall, and then their boy was really tall, and then similarly their woman or their girl or another children will be also taller than the average value. So in this case, even after we consider minus value and plus value, so in this case minus 3 centimeter, and this case plus 3 centimeter, but in terms of this minus negative and positive biases, it is towards more than the value of 165. Right. So in this case, even if we compute this y minus mu y, altogether after summing up over all the y's, so all the y's, then this value will not be 0 value because it's no longer centered at the true mean 165. Okay. So in that case, they are positively correlated, and in that case, this covariance value will not be 0. So I think this is a quite important concept that you have to be careful about. Okay. Any questions about this? 네. 나도 이 선형대수는 영어가 맨날 빠졌는데 이거는 뭐 설명이 어렵네요. 얘도 생각나는 데는 들지만, 네. 하여튼 이게 보면 이게 probability distribution이 이제 XY가 이제 인디펜던트하다, 이제 인디펜던트하지 않다, 뭐 이런 거랑 좀 관련이 되어 있고요. 이제 XY를 항상 이제 두 개를 페어로 뽑는 거를 항상 생각을 해요. 왜냐하면 우리의 이벤트 스페이스는 하나짜리를 생각하지 않아요. 우리의 이벤트 스페이스는 항상 이 페어로만 존재하고 있어요. 이 페어에 대한 각각의 이제 확률들이 있는 거예요. 각각의 확률들이 있고, 이게 우리가 그 컨디셔널 프로바빌리티를 생각을 해보면 그냥 여기서 아무 남자나 아무 여자나 뽑아갖고 이 둘의 저기 그 디스트리뷰션 생각을 해볼 수가 있죠. 근데 그 컨디셔널 프로바빌리티는 남자를 예를 들어서 185짜리를 뽑았어요. 근데 여자는 뭐 그냥 뭐 그냥 자유롭게 뽑잖아요. 이 처음에 185짜리를 뽑았든 말았든 전혀 상관이 없잖아요. 그러니까 이 디스트리뷰션은 그때 우리가 statistically independence가 뭐였죠? 마지널도 같아야 되고 x가 뭐였든지 간에 x가 185든 165든 뭐 150이든 뭐 1m든 다 상관없이 이 probability distribution이 그대로 유지가 되어야 이게 statistically independent 하다는 개념이었어요. 그죠? 사실 이 statistically independent 하다라는 개념이 이거보다 훨씬 더 스트릭트한 개념이긴 해요. 네, 이거는 조금 다른 얘기긴 하지만 일단 우리가 생각하기에 statistically independent 하다라는 개념은 지난번에 배웠고 그거를 이 경우에 비추어서 한번 생각을 해보면 일단은 그래서 남자를 뭘 뽑았든 여자의 디스트리뷰션은 항상 여자의 디스트리뷰션이 뭐 165cm를 기준으로 한다. 그러면 165를 기준으로 이렇게 가우시안 디스트리뷰션은 뭔지 다 알죠? 네? 지난번에 가우시안 디스트리뷰션이 뭐냐라고 하고 네, 네. 뭐라 해야 될까? 문화적 충격을 받았다 그럴까? 하여튼 네. 나 스스로 반성하게 됐는데 네? Gaussian distribution. So the Gaussian distribution is another name of a normal distribution. 정규 분포를 이제 Gaussian distribution이라고 해요. 이제 대학교도 보면 이제 고등학교 때 배운 말이랑 좀 다른 말 써야 좀 멋있어 보이잖아요. 똑같은 말. 그러니까 이제 뭐 C 대신에 괄호도 쓰고 이러잖아요. 컨비네이션. 그렇기 때문에 이제 뭐 어쨌건 Gaussian distribution이라고 부르고요. 어쨌건 165를 기준으로 하는 Gaussian distribution이 그대로 유지가 돼요. 남자를 185를 뽑았든 165를 뽑았든. 그죠? 이런 경우는 남자를 딱 고정을 시켰을 때에 남자를 185로 고정을 시켰을 때에 자 이게 자 이 식이 의미하는 건 뭐냐면요. 이 식이 의미하는 거 혹은 이거가 의미하는 건 뭐냐면 일단은 x가 바깥쪽에 있고 y가 이 안쪽에 있죠. 이거 구현하려면 어떻게 되죠? 우리가 이제 컴퓨터로 짜려면 for loop 2개 쓰잖아요. for loop. 그죠? 그리고 뭐 ICPC 뭐 이런 거 혹시 관심 있는 사람 없어요? 그런 사람들이 for 하나에 참 목매는 거죠. for. 그냥 그 계산 복잡도 이런 걸 결정을 하니까. 어쨌건 그것도 딴 얘기고. 어쨌건 이 경우는 지금 보면 for loop으로 우리가 이걸 구현을 한다라고 하면 x를 일단은 고정을 그러니까 x가 예를 들면 뭐 180cm, 185cm, 175cm 이 세 가지 밖에 없어요. y는 뭐 예를 들면 뭐 160cm, 165cm, 170cm 밖에 없어요. 뭐. 네, 지금 그러면 이건 어떻게 계산하냐? 175일 때 고정을 시켜요. 그 다음에 160, 165, 170일 때에 요 이널 룹을 돌죠. for I equals 요거 그 다음에 한 칸 인덴트 해갖고 인덴테이션 해갖고 j equals 어쩌고 저쩌고 이렇게 쓰잖아요. 그죠? 그러면 x가 이렇게 하나로 고정이 됐을 때의 이 값, 그러니까 요 안에 거를 계산하고 그래서 얼마가 나왔어요? y가 미안해요. 다시 x로 돌아가서 x가 이 값으로 고정이 시켜졌고 그 다음에 또 이 값을 또 계산하는 거예요. 그래서 또 계산한 나온 값, 또 이거 고정해갖고 나온 값 이렇게 하는 거잖아요. 그죠? 그렇게 되면 자 아까 내가 185, 뭐 180 이런 얘기를 한 게 남자를 일단 180으로 고정을 시켰다고 해봐요. 180으로 고정을 시켰다고 해보면 이 여자 파트에서 160, 165, 171 확률이 그러니까 애초에 그러니까 남자가 175, 180, 185 이거 상관없이 여자의 평균이 165라고 했다고 쳐봐요. 165라고 했다고 치고 남자에 대한 정보가 없이 여자만의 디스트리뷰션이 이거라고 쳐봐요. 이게 우리의 마지널 디스트리뷰션이에요. 그래서 다시 우리가 좀 두서가 없긴 하지만 이 마지널 디스트리뷰션은 따로 존재하는 게 아니에요. 지금 왜 그러냐 하면 이거는 우리가 이벤트 스페이스가 항상 조인틀리 분포가 되어져 있다고 생각하는 거죠. G of X, Y의 어떤 스페셜 케이스라고 얘기했죠. 그 다음엔 항상 거기서 시작은 이거였죠. F of X, Y. 그죠? 그래서 우리는 그 어떤 다른 디스트리뷰션도 일단은 존재하지 않고요. 우리가 주는 정보는 일단은 요놈이 확률 쪽에서는 요놈밖에 없는 거예요. 단서. 요거 하나를 가지고 마지널도 구해지고 컨디셔널도 구해지고 다 구해지는 거예요. 지금 무슨 소리냐? X가 남자가 뭐 예를 들면 175 그리고 여자가 160일 때 확률 값이 뭐 한 10%, 뭐 180이고 165일 때 확률이 뭐 15%. 이런 joint probability 테이블이 있거나 아니면 지난번에 봤던 뭐 이렇게 컬러풀한 이상한 산 같은 모양이 있었죠. 그게 일단 하나가 탁 정해진 거고 그거를 한쪽으로 압축 또 다른 쪽으로 압축하면 거기서 나오는 게 marginal distribution이에요. 오케이? 그 marginal distribution을 그러면 거기서부터 구하고 나면 그 구하고 났을 때의 평균값이 있어요. 평균값. 그죠? 즉 여자의 이 평균값이 있는 거예요. 남자와 여자의 이런 한창을 있었는데 남자 축을 없애버린 거죠. 그랬을 때 그 평균값이 165라고 하고 이게 marginal distribution의 평균값이에요. 그 다음엔 이제 요 μi, 그러니까 다시 여기로 돌아와서 x를 예를 들어서 181대로 고정을 시켰어요. 그 다음에 요거가 디스트리뷰션이 이 165, 요 값은 변하지 않아요. 요게 marginal mean이에요. average value. 그랬는데 181대 여자의 디스트리뷰션이 정확하게 165를 기준으로 이렇게 생겼어요. 그러면 이때는 이 이게 180을 기준으로 했어요. 그러면 181대 이게 평균이 뭐 한 남자 키가 175라 그러면 좀 5cm 높아졌죠? 높아졌나? 하여튼 그러면 이게 5cm가 여기서 생겼어요. 5cm가 항상 상수로 곱해져요. 일단은 요 안에선. 왜냐면 x는 변하지 않으니까. 그러면 요 y에 대해서 요 값을 한번 보자고요. y에 대해서. 그 5 곱하기 이제 준비가 됐어요. 요 물음표가 뭐냐? 이널룹. J로 도는 이널룹에서 계산을 하되 이게 이런 디스트리뷰션을 가졌다면 이거에 대한 이 y 빼기 뮤 y의 평균값은 뭘까요? 이게 0이 나오게 되는 거예요. 0이 나와요. 베리언스랑 달라요. 베리언스 이거 제곱을 해서 더 평균 낸 거고 네. 우리가 가평균하고 뭐 이런 거 할 때 가평균 우리가 정확하게 때려 맞췄으면은 항상 가평균 빼면 0이 나오잖아요. 그죠? 즉 그 말은 그 x 밸류들에다가 정확한 그 평균들을 빼고 나면 그거의 합은 무조건 언제나 0이 나와요. 그죠? 그래서 이 안에 이널룹을 J에 대해서 돌려도 어차피 0이에요. 그렇기 때문에 0 곱하기 5cm가 되는 거예요. 그러니까 5cm가 무용지물이 된 거예요. 그러면 5cm에서도 무용지물, 뭐 저기 185는 175 빼면 여기가 10cm나 돼갖고 이제 크게 값을 곱해줄 준비가 돼 있었는데 그 경우도 여자의 디스트리뷰션은 요지부동 이렇게 생겼어요. 그러면 역시 true mean을 중심으로 항상 이게 디스트리뷰션이 여기에 중심이 되어 있기 때문에 역시 0이 나와요. 그렇기 때문에 이 이널롭이 아예 항상 0이 되는 거예요. 근데 아까 예를 들어서 아까 예를 든 게 잘 전달이 되는지 모르겠는데 이게 항상 우리가 부모님이 있고 그 부모님이 항상 딸 아들만을 이렇게 항상 낳아요. 어떤 자연 생물학적인 법칙에 우리의 세상이 그렇다고 쳐봐요. 그러면 딸 아들을 이렇게 그러니까 우리가 딸 아들 혹은 남자 여자의 키를 이제 샘플링 할 수 있는 이 스페이스가 이 어떤 동일한 부모로부터 나온 남자 여자를 이렇게 샘플링 하고자 하는 그런 이벤트 스페이스 및 그거에 따른 probability distribution 혹은 여기선 저 정황은 joint probability distribution이죠. 왜냐하면 이벤트 스페이스에서 각각의 그 인스턴스들이 페어를 의미하니까, 그죠? 이 경우에는 각각의 페어에 대해서의 probability distribution이 어떨까를 생각을 해보면 x가 이제 185라 그랬다. 그래서 예를 들면은 뭐 남매가 있어서 이제 남자를 봤더니 키가 무지 커요. 뭐 당연하게 여자도 키가 크겠죠. 그 확률이 높겠죠. 그죠? 그리고 뭐 아마도 부모님이 커서 그러니까. 그러면 요 놈의 디스트리뷰션, 그러니까 남자가 185일 때, 즉 포룹이 I, J 두 개 있다 그랬잖아요. I가 이 185로 고정이 돼 있을 때에 이 안에 거 Y에 대한 포룹은 즉 요 차이는 Y 빼기 뮤 Y는 요 뮤 Y는 여전히 똑같아요. 165라고 하는 마지널 디스트리뷰션에서의 평균을 기준으로 봐서 이게 이 165에서 아까 그렸던 이렇게 이제 디스트리뷰션이 165보다 저쪽으로 간 거예요. 그러면 이건 마치 가평균, 이 165를 우리가 빼갖고 그거에 대한 그 차이를 다 더해갖고 하는데 그 더한 값이 0이 더 이상 안 나오겠죠. 왜냐하면 185일 때, 그러니까 남매에서 그 남자 형제가 185일 때는 여자 형제의 그 디스트리뷰션들을 다 이제 그 여자의 키들을 다 모아보니까 165인 그냥 아무 단수도 없었을 때 여자 키의 평균이 뭐 예를 들면 165에 비해서 디스트리뷰션이 더 큰 쪽으로 시프트 되는 거죠.
그럼 이 경우에는 인디펜던트 아니에요?
이 경우는 인디펜던트 하지 않고요. 이 코베리언스 값이 0이 안 나와요. 왜냐하면 뭐 예를 들면 10cm로 대기를 하고 있었고 이 안에 거를 계산해 봤더니 아까는 다 0이 나왔었는데 뭐 이번에는 0이 안 나오는 거예요. 그 가평균, 그러니까 뺀 평균 값이 얘가 가진 실제 평균이 아닌 거예요. 그렇기 때문에 이 코베리언스 값이 네, 이 특정 이동은 양수가 나와요. 양수가.
그러면 그 두 개가 인디펜던트 하면 0이 나올 수밖에 없는 거예요.
네, 그게 그렇게 돼요. 그러니까 지금 그래서 뒤에 나오는데 이 코베리언스가 0이 될 때를 우리가 그거를 뭐라고 부르냐? 그것도 이름이 있어요. uncorrelated라고 불러요. uncorrelated. 관련이 없다. uncorrelated. 그러면 이제 independence와 uncorrelation, 그러니까 uncorrelatedness와 independence와의 관계를 보면 independence는 무조건 uncorrelated를 그걸 해요. 그러니까 두 개가 더 어느 게 더 빡친 조건이냐? independence가 더 빡친 조건. independence는 당연히 uncorrelated고 그러나 uncorrelated면 independence가 되지는 않아요. So again, so if this covariance is not zero, okay? So so there could be two cases where the first one is this covariance is non-zero and the other is zero. So if they are non-zero, then this x value will actually influence or give some biases on your distribution of y, so that this inner loop of the summation of this guy become non-zero. But in the case of this covariance being zero, then this distribution is always remains the same. So in that case, this covariance value will become exactly zero. But what about this? So let me give a little bit more interesting example that can burn your brain. So in this case, it's all about the mean, right? And there are differences from the true means, right? So in this case, so let me just add another page. So if x was 185 centimeter, then so the true mean was 165 for y value, then this guy. So in this case, and then 170 centimeter, and then also the distribution for woman's height will remain the same. In that case, they are uncorrelated because they are not biased from this temporary mean. Okay, so this was actually the marginal mean, and then they work as the temporary mean because y minus mu y. So y can be considered as this conditional situation where x is a set or fixed as 185, and then the distribution of y, whether that distribution is biased with respect to the true mean. So that determines whether this covariance value is zero or not. Okay? But what about this? So in these two situations, they will generate zero covariance, which we call uncorrelated. But what about this? So in this case of 185 centimeter, then the distribution gets a little bit wider. But still they are centered at 165. But what about this? In this case, the distribution 165. So they are still exactly centered at 165, but that distribution is really sharp. Okay? So mathematically, this is the distribution of y given x equals 185. And in this case, this is y, and this is 170. So in this case, what will be the covariance value? Would the covariance value be still 0 or not? 0. Non-zero. So this should be 0. Okay? Because they are still centered at 165. Okay, so this is not like 165, and then the distribution is something like this, and then their average value, the true average value given x equals 170, and then the true average value conditioned in this situation is really different from the true mean value of y, right? So in that case, that generates non-zero covariance, right? Like covariance might be like 3 or 5 or something like that. But in this case, even though the distribution, I mean their shape, overall shape is different, but they are still centered at 0. So if we take the y minus mu y, which is just like computing the difference from our true the observation y minus the temporary mean of mu y. So if this still gives a 0 overall, and then they will be still uncorrelated, which means the covariance value is 0. But in this case, let me ask another question. So in these two cases, are they statistically independent or not? Independent, statistically independent between x and y. Not independent. And why? Why? 왜 그러죠? 한국말로 대답해도 돼요?
x에 따라 바뀌었잖아요, 모양이.
그렇죠. 그렇죠.
Yeah, so he gave an exact answer. So in this case, the distribution itself, I mean the probability distribution, actually changed. Even though their mean remained the same, but their shape, I mean they are certainly different distribution, right? It has more or wider variance than this guy, right? So that means x value actually influenced the distribution of y. So that means the conditional distribution of y, depending on what the value of an x is, they will change. In that case, it doesn't satisfy the condition for statistically independent, right? So that way, I mean, if the two distribution has the exact same shape, then they will be statistically independent. But still, in this case, even if they are not independent, they can still have 0 covariance, which means uncorrelated, right? So that's why I mentioned that independence is more strict concept than this uncorrelatedness. Okay? So yeah, we can even think about this type of distribution, something like this. Okay? So this type of distribution will still have the same mean of 165. So they are not biased, right? But the distribution, the shape of this distribution drastically changed. So that way, in this case, they are uncorrelated, but they are not statistically independent. Any other questions? So this is really important notion. So, okay, then this covariance is also computed in this form. So this formula gives a more convenient way of computing this variance, I mean the covariance. So in the covariance case, so we always have to subtract this mean of an x and y from the original x and y value, right? So that is kind of annoying, right? But in the case of this, so we just simply consider or compute the expectation of an x times y, which means, so in the case of 185 and then 175 for man and woman, in that case we had to take subtract the mean value, 175 and minus 165, so which means 10, 10. Okay, so in that case 10 times 10 will be the value corresponding to this value, right, which is the value of our function of g of x comma y, right, x comma y, and this function value, right? But in this case we just need to multiply 185 times 175. Okay, although this look a little bit more computation than this, but in many cases we just compute this value is much faster than computing this values. So this equation or formula can be utilized in that manner. Okay, then the next one is this the notion of this correlation coefficient. So correlation coefficient is, so this is how we compute this correlation coefficient. So we know how we compute this covariance of an x and y. Okay, so again the covariance is defined in this form. Then let's see. Then we just simply divide it by the standard deviation of an x and the standard deviation of y. Okay, so we first compute the variance of an x and y separately, and then take the square root, and then we divide this covariance value by those two numbers of standard deviation of an x and y, and that is called this correlation coefficient. And this correlation coefficient has an interesting property. So they always lie between -1 and 1. So that's an important kind of a concept. Okay, so so if they are 1, then they are perfectly correlated or perfectly positively correlated because their correlation is 1. And if they are -1, and then they are perfectly negatively correlated because their correlation is -1. So let's see. Okay, so in the case of previous example of a boy and girl who were born from the same parents, in that case, would they be their height be positively correlated or negatively correlated? So again, the question is. Okay, so the question is. So yeah, let's consider the two cases. So now this one is non-zero, but this one can be positive number and negative number. So when it will be like this value is positive number. So in that case, back to the example. In this case, 185 minus 170. So in this case, we picked up the person or the man who is taller than the average height. So in that case, if this distribution of y or the woman's height, it could be 165. Yeah, it could be positively biased or negatively biased. Okay, so in this case, let me see. So yeah, your parent has a really lot of money. So your parent is really rich. Okay, and then you are not the only child. So you have another brother or sibling, and then all the total amount of money that your parents have will be distributed between those two. So if your sibling or your brother received a lot of money from your parent, and then there will not be much money left that is given to you, right? In that case, based on the assumption that roughly the total amount of money that your brother and you will receive from your parent is fixed. In that case, suppose you observe that, okay, so you don't know yet how much you will receive from your parent, but you already know because your brother actually called in the morning that, oh, okay, I received this amount of money from your parent. Okay, in that case, you can kind of guess how much you will receive from your parent, right? And then what we are interested in is that are they really positively correlated or negatively correlated? Which means if you observe that your brother actually received a lot of money, and then you will likely receive really small amount of money, right? Although it's a really sad situation, but yeah, we wish our parents is really fair, but that might happen, right? So in that case, if we observed this x value as really high value than the average value, and then it means my own value, or in this case, the woman's height might be much lower than the average value. So in that case, they are kind of inversely correlated or inversely proportional, roughly. So in that case, they are negatively correlated, and then in that case, this covariance value will be minus value. Okay. So in that case, so from the perspective of double for loops of x and y, so this one was 185, which had a positive bias from the average. So in this case, 185 minus 175, which was plus 10 value. Okay. In that case, this distribution y minus mu I, if this was this, and then y minus mu I will be positive value. So this positive value and this positive value will altogether be multiplied to generate the positive value. But in the case where this value is now biased towards the negative value compared to the true mean, something like this. In this case, overall the inner loop of j equals 170, 175, 1 and so on for woman's height, and that value will overall generate minus value, negative value. So positive value times negative value will generate negative value, right? So in that case, if they are negatively correlated, then this value will have negative value. Okay, so you guys now know the meaning of positive correlation and negative correlation, and then how much they are correlated or how much they are not correlated. So how much they are uncorrelated or they are strongly correlated, that is determined by this correlation coefficient, because this value is, always lying between -1 and 1. So I cannot give a really rigorous proof about why it should be, but after you divide this covariance with these by the value of standard deviation of x and y values, and then this value will always be between -1 and 1, and then if it is 1, and then in that case, it only works. I mean, in that case, this is always the true. Y is always the linear relationship with x, where x, a is positive number. Okay. So if y is obtained exactly as a function of an x as this linear relationship, this is not actually a linear relationship. This is called affine relationship because we also have this bias b. But anyways, in this specific case, we can prove that this correlation coefficient or this covariance value divided by the standard deviation of x and y will be always 1. Okay? But we cannot easily prove that if this covariance value is 1, and then this will always satisfy this case. So we cannot prove that. So we cannot easily prove this direction, but we can really easily prove this direction. Okay? And then similarly, in the case of -1 as the correlation coefficient, then it is actually the same as this linear relationship. But in this case, a should be negative value. So if y satisfies this relationship with the x, and then this will satisfy -1. Okay? Okay, then now let me just add one final explanation so that we can a little bit more easily understand what this correlation means. So we kept thinking about this example of men's height and woman's height, right? And then we always get a pair of men's and women's height, right? And then why not just drawing these samples in our 2D plane? So this is an x value and this is a y value, okay? So what is this relationship? So if the man's height was 175 and then woman's height was exactly 168, for example, and then 180, and then it was something like 163, for example, okay? So in this case, if y is always existing along this line, it doesn't matter what this line is. We only know, we only care about the direction or the sign of the slope. So if y is exactly having the relation as this, and then this one corresponds to this case, okay? And in this case, let's think about the probability distribution. So suppose, so let's consider this probability distribution. Okay, so what is this conditional probability distribution looking like? So what does this probability distribution look like? So suppose x is fixed as 180, and then the y value is always having this 163, right, as the value. So there is no other possible values for y. So in that case, the probability distribution for y is having this kind of shape. So 163, something like this. Okay. So there is no other possibilities having other values than this 163. Okay. So in that case, so in this case of 2D plots, so let's think about how we can generate from these 2D plots for our joint probability distribution. Okay, so so here the situation is that you don't know the probability distribution at first. You don't know the true probability distribution or how we can write their mathematical distribution at all, right? But you only get a samples from some unknown probability distribution. Okay, so it will be like you just sample the brother and sister's height jointly from our South Korean population, and then you will just mark those points. So 175 and 160 and 180 and 163 and somewhere around So we no longer consider this linear relationship. We just think about the general relationship. So in this case, so this is a man's height and woman's height, and then something like this. So we get this kind of samples from our unknown probability distribution. Okay? Okay, then let's see. Here we see 185 centimeter, for example. Okay. So let me add more samples. Okay, so in this case, so this one is actually your joint probability. So this is our sample, but we can think about their histogram, like three-dimensional histogram. So we just divide this range into this grid. Okay. Okay, and then we can think about the height of the bar, where the bar height is actually proportional to the same as the number of the points or the samples that we obtained corresponding to that rectangle. Okay, then we can think about the three-dimensional bar graph, and that bar graph is actually your joint probability distribution, right? And if we get more and more and more samples, and then that histogram or that bar graph will actually approximately be the same as your true probability distribution. right? And then, in this case, so yeah, their continuous version is actually the same as what we saw in the previous lecture about like a really beautiful shape of this colorful 3D kind of mountain-like graph. Okay. Okay. So in this case, so in the case of 180 centimeter, suppose we want to obtain this guy, 185. So in this case, what would that be? Yeah, before we get the true probability distribution. So this is an approximated probability distribution for joint density for x and y, right? So that means, so this probability distribution is something like this. So we get this type of bar, okay, where this x value is fixed as 185. And then if we look at the slice from this direction, and then it's a really 3D, so it will be like this kind of distribution, right? So that will be like a surface. And that surface, I mean, that graph or that curve is actually your conditional probability distribution, right? And then what about this? So what if we sample 165, for example? So in this case, and then what would the surface at that point look like? So in this case, something like this, okay? So we definitely saw that the mean value has changed from a little bit higher value, right, to a lower value in terms of a y value. So probability distribution actually changed, right? So this is basically uncorrelated situation. Correlated situation. So the covariance value will not be 0, right? Then, okay, so yeah, so if we think about the surface, and then, yeah, they are correlated situation, and then what would be the sign of the correlation, or the covariance value? So would that be negative covariance value or positive covariance value in this case? So as x becomes larger, the bias or the actual their conditional mean value will be shifting to larger value, right? From this value to this value. So definitely, as x increases, y also has increased, right? So that way, in this situation, the covariance value will be positive value. So if we just look at their samples and their distribution or their kind of cloud, and then we can immediately say that, oh, okay, this is positively correlated, or in this case, the covariance value has the positive value. Okay, but what about the negative value, negative covariance value? In that case, it will be something like this. Although it's a little messy, but yeah. Yeah, so in this case, definitely we can kind of see this type of a rough trend or pattern, right? So in this case, once you compute the covariance value, and then in that case, the covariance value will be negative value. Okay, so from this just simple 2D like sample plots, then you can just roughly, yeah, and also immediately say that the sign of this covariance value. And what about the uncorrelated situation? Uncorrelated situation is that whenever you cut, I mean, wherever you cut, at this point or this point or this point or this point, their mean should be remaining the same. In that case, the covariance becomes 0. Okay, I think that's yeah, that was about the covariance and the correlation coefficient. And then, yeah, back to this figure. If we see exact like a linear relationship like this, and then this, in this case, this one is perfectly correlated, and this one has always the correlation coefficient as 1. Okay, but what about this? So suppose this graph was x plus 2, for example, but what about this? So what about this? So we know that this has the correlation coefficient as 1. So what about this? What would that be for the correlation coefficient? Would that be like 3 or 1/3 or can anyone answer? Correlation coefficient for the second one, where we have this exact linear relationship. Positive, but exactly what value? So again, in this case, so the reason for having the correlation coefficient as 1 is because when x has maybe 185, it has exactly a single value, right? In terms of a probability distribution, it was like something like this, right? From looking at the surface. At this point, it also has the probability of like this, right? In this case, the correlation coefficient is 1. So in this case, all the situation is the same except that the slope has changed, and also the bias as well. So in this case, the correlation coefficient will still remain as 1. Okay.
정확하게.
네, 둘 다 정확하게 1이에요. 정확하게 1. So if they are exactly in the linear relationship, and then it doesn't matter how steep is, your slope is. If they are exactly linear relationship, and then the correlation coefficient will become exactly 1. But what about like 0.98 or 0.85, which is quite strongly correlated towards 1, but they are not perfectly 1. And what determines that aspect? So if this correlation coefficients are degraded or gets lower from the perfect value of 1, it means this sharp distribution. So perfectly sharp distribution has a little bit of a leaking towards these neighbor value. Something like this that has like a non-zero variance. So in this case, the point cloud. So point cloud means like if we mark all the points and then in the densely marked region, and then they will be looking really dark, and then like a sparsely marked region, and then they will be roughly roughly white. So in this case, the point cloud will be something like this. So they are always really, they almost really sharp, okay? But they are not exactly along the line. They have a little bit of a leaking or some kind of a point that are a little bit off from the exact linear this path, okay? So that way, so intuitive meaning at this point about the correlation coefficient is that how sharp they have this kind of a linear relationship, regardless of the height, okay? Regardless of the slope. So slope doesn't matter. So if they are really along the line, and then there is a really small or no leakings out of this linear relationship, and then they will really have a high coefficient, correlation coefficient. But if they are really off, like this, so even if we can obtain this kind of a representative line, but in this case, they will have some correlation like a 0.6 or 7 or something like that. Okay, so that's it for today. So we'll continue this Wednesday. Okay.